So hello everyone, and thank you for joining us for the Physics Hour, a new weekly event to explore different fields of research in physics and ask leading scientists some of your burning questions. My name is Simone, and we also have Valentina here to help with the Q&A after the talk. Before we begin, many of us are likely to be tuning in from different places, but I'm coming from Montreal, which is situated on the land which has long served as a site of meeting and exchange amongst Indigenous peoples, including the Haudenosaunee and Anishinaabe nations. I acknowledge the diverse Indigenous peoples whose presence marks this territory from which I'm joining you today, and encourage everyone to learn more about the land that they live and learn on through the links posted in the chat. The Canadian Association of Physicists is the voice of Canadian physics, representing physicists in all parts of their careers. The CAP provides leadership and support to the Canadian physics community by celebrating Canadian physics achievements, keeping members up to date, and by running various initiatives like the ones you see below. The CAP's Student Advisory Council was formed in 2019 to create a strong student voice within the CAP. We're an egalitarian, diverse, inclusive, and action-oriented group which seeks to represent, support, and unify physics students across Canada. Some initiatives we're currently working on include advocating for increased student funding, advertising student opportunities through our website and social media, and interviewing physics students across Canada to understand how we can best serve the community. If you're interested in learning more about what we do, I encourage you to browse our website. We represent all physics students in Canada, so please get in touch with us through our email or social media and share your voice. Now, I'm very pleased to welcome today's speaker, Professor Randy Lewis.
Thank you very much. Let me get my screen shared so you can see some slides. Okay, hopefully you can see my slides. Let me know if there's any problems along the way. And thanks very much for including me in your list of speakers. It's great to be here. I'm really looking forward to our discussion. I hope you'll have lots of questions for me, and I hope that you will find this topic interesting. You see the title at the top of the screen, Using Quantum Computers to Simulate Elementary Particles. I want to begin by saying how we normally use regular computers for calculations of elementary particles. And that will lead us into asking, why might you want to try this with a quantum computer? And then what is a quantum computer and how could we possibly do such a thing? And that will lead us toward talking about some work that my students and I have been doing recently. So to begin, I don't want to talk about all kinds of different elementary particles. I want to talk about the most difficult ones. And what I mean by most difficult is the ones that feel the strong force, sometimes called the strong nuclear force. You know that people often say there are 4 fundamental forces in nature. There's gravity, there's electromagnetism, there's the weak nuclear force, and there's the strong nuclear force. The special thing about the strong force is that it's really strong. So all the other ones are weak or feeble forces. That means that the interaction between 2 particles is somehow small. And therefore, you can do a Taylor series expansion in the small parameter. People often call this perturbation theory. That's an easy and very valuable way to do many calculations in electromagnetism, in the weak force, and in gravity. But for things like quarks and gluons that feel the strong force, we can't use that method. And then the standard thing to do is to just put it on a big computer and do the calculation directly, not assuming anything is particularly small. So the picture that you see here gives an example. Suppose you wanted to understand the properties of a proton. You are made of all kinds of protons. Everything around us is made of protons and neutrons with the electrons orbiting them. But the world inside of a proton or inside of a neutron is really complicated. There are many quarks and many antiquarks and many gluons doing all kinds of things inside the proton. Suppose this blue circle that you see represents the proton. There's nothing weak, there's no small parameter that we can take advantage of inside that complicated environment in the blue circle. So what people will do is just take a big computer and divide all of space and time up into a grid or a lattice. And then you'll calculate, using quantum physics, all of the quantum phenomena that are happening on every little site and every little link and every little square all over this entire lattice. And you'll do that according to the laws of the standard model of particle physics. And since it knows what quarks and gluons really do, that's all you need to do. Calculate all over this giant lattice to learn what the properties of a proton are. So just to be really clear, if we zoomed in on one little square, people tend to call these squares plaquettes. So if I zoom in on one little plaquette, here's what we're talking about. There's a quantum field at every site, shown in green here, for the quark. And there's a quantum field on every line segment that joins the two sites for a gluon. You can picture this as the gluons gluing the quarks together and forming this really tight binding, which makes the proton. This is something that people have been doing for decades. It works extremely well. It gives us our most precise and most accurate properties of what quarks and gluons do inside particles like protons, neutrons, pions, and any of the other particles you may have heard of that feel the strong interaction. So if this all works so well, why should we care about quantum computers? Well, although the picture I drew looks like a three-dimensional lattice, actually people do calculations on four-dimensional lattices. It has a length, a width, a height, and a time direction. Or to be even more precise, it has an imaginary time direction. What I mean is simply the time you would measure on your wristwatch multiplied by the square root of -1. In other words, I. So that makes it an imaginary number. Now, at this point, the obvious question is, why would you do such a crazy thing? Everybody wants time in normal units, like seconds or minutes. Why would I want imaginary time? And the answer is, well, I don't want imaginary time. However, what we have to do is essentially do integrals over these quantum fields numerically on the computer by using the lattice method. And it turns out that these numerical integrals that you have to do really don't converge if you're using a standard numerical approach, unless you use imaginary time. In imaginary time, actually, the integrals will converge quite nicely. So that sounds like good news, except that you can only calculate properties that you can write down with imaginary time. Let me give you some examples. If you want to know the mass of the proton, or if you want to know the shape of the proton, these are static properties. Time isn't really important, and you'll do an excellent job with the traditional lattice approach of getting static properties of the proton. But if you're interested in dynamics, for example, you like the Large Hadron Collider, where they have giant beams of protons approaching each other and colliding. This happens in time, right? It happens in real time. It does not happen in the square root of -1 times time. And this is a problem. If you want to see things moving, if you want to see dynamics, the standard approach to computing quarks and gluons doesn't give you that. However, if we reformulate the problem the way we would imagine doing it on a quantum computer, we don't have to use imaginary time. We could use real time and we could see actual dynamics. There are other reasons to use quantum computers as well, but this is one of the easiest and one of my favorite reasons to think about using a quantum computer. Okay, so I'm starting to like the idea of quantum computers, but we should talk about what they are. So you are probably watching this video happen right now by looking at a computer. Your computer ultimately does all of its calculations in terms of bits, the tiniest bits of information. They are ones or zeros. Each bit is on or it's off. I imagine it to be like a light switch on my wall over here on the left. You can put it in the up position or in the down position, 2 options. That's a standard classical bit. Quantum computers, though, use quantum bits, usually called qubits. Here, we can have our qubit in the state 0, or up, or on, if you like. We can have it in the other option named 1, or down, or off. But it could also be in a superposition of these two. That's a quantum principle. Now, for me to imagine what that means, I picture a quantum bit or qubit not as a light switch on my wall, but as 2 dials on my wall. Of course, qubits are really not 2 dials on your wall, but this just helps me understand, visualize what this means. So to get 1 qubit, I'm going to use 2 dials. And here's the expression. Some of you may recognize something like this from quantum mechanics. This is the expression that I get from my 2 dials. So for example, you might grab onto the theta dial and rotate it around so it points to the angle 0 degrees. In that case, we would be taking the cosine of 0, which is just the number 1. And we'd be taking the sine of 0, which vanishes. So in that case, we would only have the first term. That tells me that when you choose the theta dial to point in the direction of 0 degrees, our qubit is in the state named 0. So the 0 state. Maybe it's like having my light switch up. On the other hand, if you take the theta dial and you turn it around so it points in the opposite direction to 180 degrees. Now we're taking the cosine of 90, which vanishes. We're taking the sine of 90, which is 1. So we get this other state. It's as though the light switch is down. Interestingly, it's multiplied by some funny complex phase. And the value of that phase depends on what you chose to do with your other dial, 5. Now, in general, you won't choose theta to be either 0 degrees or 180 degrees. You'll make some other choice, and then neither the cosine nor the sine vanishes. And so you'll have some superposition of both on and off at the same time. This is quantum mechanics. And you remember how the story goes. We can have our qubit at any moment in some superposition of both on and off. But when you measure the qubit, you will find that it is either on or it is off. You will never measure the superposition. The wave function has changed. People say the wave function has collapsed by the very act of you measuring it. And so we have this interesting situation in a quantum computer. In a classical computer, my qubit has exactly 2 options. It's on or it's off. In my quantum computer, my qubit has an infinite number of options, an infinite number. But after I measure it, it has one of 2 options that it can choose. And the coefficients out in front, the cosines and sines, tell me exactly what the probability is that it will choose this option or that option. If I have 5 bits in my classical computer, I have 2 to the power 5 options. All 5 light switches could be up, all 5 of them could be down, 2 could be up and 3 could be down, and so on, 32 options, 2 to the 5. If I have 5 qubits, I have a huge infinite number of possibilities, but after I measure, I will get one of the 32 basis states. So it sounds on the one hand like there's a lot of potential inside quantum computers, but we have to think very carefully about how we get the information out by measuring the results and collapsing these wave functions. It sounds like a great idea, at least to me. The problem, though, is this is not a real qubit. I want a real qubit. I want something that's actually quantum, not just imaginary dials on my wall. Are these qubits something that I can build myself from things I have around the house? Yeah, actually, in a sense, they are. Not in any practical sense, but an electron is a spin-a-half particle. It can be either up or down. An electron could be a qubit. A proton is a spin-a-half particle. It can be up or down, or of course, a superposition of the two. But a neutron could be spin up or spin down. Atoms can be spin up or spin down. Certain kinds of atoms are spin 1/2 atoms. There are all different kinds of things that would act like a qubit. But remember, you want to be able to control your qubit. You want your qubit to work for you. You want to be able to rotate it around the z-axis. You want to be able to rotate it around the x-axis. You want to entangle one of your qubits with another qubit. You don't want it entangling with the box it's in or something beside it. And this is the issue. So where can we get qubits? In principle, any two-state quantum system can be a qubit. But you want something you can control. So there are many different options, and you may have heard of labs that are building their own qubits, and many different approaches are looking very promising. I just want to mention one of them. If you happen to know about IBM quantum computers, or maybe you know about D-Wave quantum hardware, they both use tiny circuits for qubits. If you go back to your introductory physics textbook, you might find an LC circuit, an inductor and a capacitor in a little circuit all by themselves. If you start this circuit with the capacitor charged, you remember what will happen. Current will flow clockwise through the inductor, and then it will flow counterclockwise, and then it will flow clockwise, and then it will flow counterclockwise. It will act like a harmonic oscillator as the energy moves from being stored in the capacitor to the inductor, back to the capacitor, and back to the inductor. If you did this with a really small circuit that's really cold, so low in energy that you start to see the quantum effects, you would notice that there are only certain discrete quantized energy levels for the energy stored in this circuit as it oscillates back and forth. It's no longer simply a harmonic oscillator, it's a quantum harmonic oscillator. So here's the potential energy. It's just a quadratic, as you remember from introductory physics. But quantum mechanics says you can have this energy level named 0, or the next energy level named 1, or the next energy level named 2, or the next energy level named 3, and so on. And those of you who have studied the harmonic oscillator in quantum mechanics remember that all these energies are equally spaced. This is more than we need. I just want to build a qubit. I should just have 2 energy level options, say 0 and 1. The rest of them we can ignore. Now, if you think about it, maybe this quantum harmonic oscillator isn't the perfect thing to use for a qubit, because we want to control this qubit. We want to control the transition from the 0 state to the 1 state. Unfortunately, that energy gap is exactly the same as all the other energy gaps that lead to states I never want to get to, since I only want my single qubit. So what people do in practice is they change the shape. It's no longer a perfect quadratic. It's bent a little bit, so the ground state and the first excited state have an energy gap that is unique. That gives you the best control over the 2 states and transitions between them that you want. And the way that's done is to replace the inductor by a Josephson junction. Now, at this point, I should remind you that I am a theoretical physicist. I do not build these things. I do not want to build these things. And the great news is we don't have to. It's nice to know the basics of how it's done, but you can log off this call right now, go make a free account, either with IBM or with D-Wave, and start using their quantum computers. They built them already, and they make them freely available to you. So that's how we're going to proceed. Here's an example of what it looks like if you're looking at qubits from IBM. In the picture on the left, you see a little circuit with 7 qubits, and you can actually count them. There's a little square right here, that's a qubit. There's another one below it, that's a second qubit, and then 3, 4, 5, 6, and 7. And you see little connections joining one qubit to a neighbor. Here on the right, you see a chip where you can't identify the individual qubits, but there are 65 of them in there. And maybe you can guess from the size of some of these features on the circuit board. This is approximately the size of a 25-cent coin or a $1 Canadian coin. So let me transition to the physics calculation that we wanted to do on these IBM quantum computers. And the work that I'm going to tell you about, you can also read in case you're interested. It was posted online. Here's the link in May, 2 months ago. And here are my collaborators, Sarmed, Emmanuel, and Sarah. These are all students at York University in Toronto. Sarmed is in the master's program. Emmanuel is in his PhD program, and Sarah is in the bachelor's program. I have to say, these are fantastic collaborators. It has been a great deal of fun to work with these people, and this is not the first project we've done together. Last year, we actually published a paper where we did calculations on D-Wave hardware. You can go look that up or send me a note if you're interested. Today, we'll just talk about the IBM project that we've done a couple of months ago. So you remember the ultimate goal. We like to dream large, right? So I'm imagining someday I'm going to run my quantum computer on these millions and millions of little plaquettes that fill an entire lattice. And I'm going to tell you about the properties of the proton and what all the quarks and gluons are doing inside of it. Today, though, quantum computers are very small with a few number of qubits, and they're very noisy. And much of what I tell you in the next few minutes is going to be an example of how we can manage this noise and still get interesting physics results out of today's qubits. So to that end, instead of having a lattice with millions of plaquettes on it, let's use a lattice with 2 plaquettes. Just a little corner of the lattice like this. Here it is zoomed in. We'll have 1 square on the left, and we'll have 1 square on the right. This is our entire system. That's what we want to study in our project. Instead of having quarks and gluons, we're going to not have any quarks. We're only going to have gluons. So there'll be some glue or gauge field on this line segment, and on this line segment, and on this line segment. All of them will have glue, but there won't be any quarks that would have been sitting at the corners. In the real strong force in nature, the strong nuclear force is sometimes called the color force. People talk of it as having 3 colors, red, green, and blue. These are not literally the colors you see, it's just words people use to describe the strong force. To keep our calculation simple, we're only going to use 2 colors, say red and blue. And finally, one more approximation. How much color charge, how much strong charge is running along this line segment or along any other line segment in this picture? we could have any quantum amount. We could have 0, we could have 1 quantum, we could have 2 quantums, we could have 3 quantums. But in our calculation, we're only going to allow 2 options, 0 or the smallest non-zero value. That's what I mean by yes, no here. Is there a minimum quantum there? Yes or no. If it's no, then it's 0. So these are dramatic simplifications that will allow us to do calculations on quantum computers that exist today. We should talk about basis states. What could you imagine the color charge doing on this little lattice? Well, one option is that we don't have any color charge anywhere. Another option is that it could be going around and around the left side of our lattice. Or it could be going around and around the right side of the lattice. Or it could be going around and around the entire lattice. And these are the only 4 options that I can imagine writing down without violating Gauss's law. This is another thing you remember from electricity and magnetism. Gauss's law says that if I draw a little Gaussian surface, the amount of charge flowing in is equal to the amount of charge coming out. If I have color charge flowing along this line and it arrives at this point, either it comes out by going downwards, or it comes into the point and comes out by going to the right. It can't just come in and disappear. Or it can't come in and suddenly we have twice as much, some going down and some going to the right. The amount of charge we have is conserved in the calculation. That's a basic property of this physics. And so we have 4 options, or, of course, any superposition of them. Quantum physics allows you to have some probability of measuring color flux here and there at the same time. So how many qubits would I need in my calculation if I wanted to study the physics of color charge, strong charge, flowing around and around on this little lattice? I could use 1 qubit to say whether the left is off or on, off or on. And I could use the other qubit to say whether the right is off or on. So 2 qubits should give me 2 to the 2, or 4 basis states. And here they are. There's a lot more physics than 4 states because of all the superposition options. Let's do a calculation. And the thing I want to calculate is time evolution. I want to watch something travel across my lattice, because that's something we can't do with the standard approach to lattice gauge theory that people have been doing for the past 4 decades at least. So here's how we'll do the calculation. If you've studied quantum mechanics, the left side of the equal sign will look familiar to you. Time evolution in the Schrödinger equation is the exponential of -I times energy times time. Or more generally, the exponential of -I times the Hamiltonian, the energy function, times time. To get to what's on the right-hand side, I'm going to skip all of the steps. There are several. You don't want to see them right now, but you could look in our paper if you're interested. For example, we have to write down what is the Hamiltonian for the strong force. Then we have to say, how can I write that Hamiltonian in terms of qubits? And then we have to say, how can I take that Hamiltonian written in terms of qubits and put it up in the exponent of something? Let me skip all of those steps and just explain what the answer means. This crazy looking symbol collection on the right. Ultimately, what you see are 2 horizontal lines, one in the bottom and one in the top. Each horizontal line represents one of our qubits. Each little box represents an operation we're doing on that qubit. So this first box says rotate the top qubit around the y-axis by this angle. Notice that the angle depends on how much time has passed. When do you want to calculate the new state? You put in the time there. And it also depends on x, which is how strong do I want my strong interaction to be? I get to choose that number. It's the only number I get to choose. And then after you're done rotating around the y-axis, rotate around the z-axis, the same qubit by this angle. And you see more x and y, or sorry, y and z rotations of that qubit. You also see some y and z rotations of the other qubit. And you see these interesting things. This is an operation that involves both qubits at the same time. It's called a controlled NOT gate. The little solid dot is the controlling qubit, and the big circle is the target qubit. So if the controlling qubit is off, don't do anything to the target qubit. But if the controlling qubit is on, flip the value of the target qubit. If it was off, turn it on. If it was on, turn it off. And that's all there is to it. If you want to rush off and try writing this code to run on IBM's quantum computers, it will not take you very long. IBM provides you with a software package that they call Qiskit, and it's written in Python. So you can write a little Python code. To put in this gate is one line of Python. To put in the next gate is one line of Python. To put in this controlling gate is one line of Python. So your entire Python code won't be very long. If you want to do 2 time steps, just do this whole thing twice, one after the other. If you want 3 time steps, do it 3 times. If you want 4 time steps, do it 4 times. All right, let's try this out. Suppose we actually run it on an IBM quantum computer. What should I expect to see? And just to set the stage, we have to determine an initial condition. So let me back up to our 4 basis states. Let's start in option number 2. Let's say we have some color flux flowing around the left side of our lattice. And then I want to wait and see, what does the strong interaction do as time goes on? Will it just sit there and have flux going around the left? Or will something more interesting happen? Quantum contributions from these other basis states may appear. So if we go ahead and do a calculation just from theory, before we go to the quantum computer, here is the correct result. The red curve is the probability that we do indeed see flux in the left half of our lattice. The blue curve is the probability that we see flux in the right half of our lattice. So at time 0, way over at the left of the graph, you see the red starts at 1 and the blue starts at 0, because that was our choice for the initial condition. But as time goes on, oscillations happen, superposition happens, and we should see all of these oscillations when we run on the IBM quantum computer. So we tried it, and let me show you what we found. Here's what we found. If you look at the left side of the graph, you see red data points that do a fairly good job of matching the red curve. And you see blue data points that do a fairly good job of matching the blue curve. But as we apply more and more time steps, more and more gates to our quantum circuit, the noise starts to build up. And eventually, these points all just hover around a probability of 1/2, which is just a coin flip. What's the probability of finding strong interaction gauge flux on the left half? I don't know, 50%. What's the probability of finding it on the right? 50%. The signal has been lost from our attempted calculation. Too many gates for today's quantum hardware to handle. Now let's play another different game here, just for fun. Actually, it's not just for fun. There's a good reason for this, but for now, pretend it's just for fun. Instead of, say, this point, the fourth red point, what we did to get that point is take 4 time steps. 1, 2, 3, 4. So we did the circuit 4 times in a row, and then we measured the answer. Suppose instead we did 2 time steps forward in time, and then 2 backward in time. The circuit is the same circuit. We just put a little minus sign in front of the time values. But it's the same qubits with the same circuit, the same gates in the same order. But of course, the answer should now be different. The answer should be what we had at time 0. We go forward in time and then backwards in time by any number of steps, and we would always get 0. Always get the value at time 0. So we should find a whole lineup of red points all at the top of this graph. And we should find a whole lineup of blue points all at the bottom of the graph. We just be measuring the answer at time 0 over and over again. We tried that on the quantum computer, and here's what we found. These points are not all at the top of the graph. They start out at the top of the graph, but of course, today's qubits are noisy. It gradually approaches a coin flip, probability of 1/2. And similarly down here, the blue data points did not start at 0. They started at 0, but they gradually ended up as a coin flip in the center. We can make valuable use of this simple observation, because here we know what we calculated on the quantum computer for both of these envelope functions. And we also know what the right answer should have been. Red always equals 1 and blue always equals 0. And it's essentially the same circuit that we were using for these other points. So shouldn't the circuits be making the same errors with our same qubits and our same gates all the time? Let's suppose that's true. Let's use this simple equation that says in our mitigation run, that's just these envelope functions. We know the numerator. Red has a probability of 1 and blue has a probability of 0. We also know the denominator. We calculated it on the IBM quantum computer. That ratio should be exactly the same as this physics run, where the denominator are these data points from the quantum computer. And the numerator is the thing we want to calculate. It's the only unknown in this equation. So let's just type in the numbers from the graph and calculate P true here, the true probability. And here's the result. This is not a new run on IBM. It's just the data you see in the top panel. And now you see red data points tracking the curve all the way across the graph. It's not perfect, but it's really, really good, much better than what it looked like up here. And the same for blue. In other words, the signal was hiding inside these points all the time. We just had to understand how to measure the errors that the hardware was making and how to account for those errors. Now, just in case you're interested, I'll mention very briefly that there are all sorts of other details that I haven't mentioned. For example, you might worry. I said that if we have this controlled gate, this entangling gate, it should behave the very same way in one calculation with forward time as it does in another one with backwards time. But is that really true? Couldn't it be, after all, that this gate makes different errors depending on whether the incoming qubits were turned on or turned off? Yeah, that's definitely a possibility. And so to account for that, we use not just this simple entangling gate, but we use randomly any of the 16 little gates that you see on this page. On a perfect quantum computer, they would all give exactly the same answer. But on our noisy quantum computer, they will randomize the noise. And that really helps us get good results. For example, look at this one. You flip one qubit and then apply your gate and then unflip the qubit. it should give you the same answer, but the input to this little gate in the center is different now because it has experienced an X, whereas up here it had not experienced an X. So these sorts of details need to be included, but then we get the results that you just saw. So finally, let me show you this graph where we come back to the physics. We spent so much time making sure we understand how to handle the mistakes, the errors that today's qubits make. But now we can turn to a discussion of physics. What can we calculate in our system? We don't have any quarks, but we do have gluons. And if you remember the strong force, it doesn't allow free quarks. Quarks are always confined inside hadrons. It also doesn't allow free gluons. Gluons have to be confined inside bigger particles. You might call them glue balls, balls of glue that are many gluons inside of them and held together tightly by the strong nuclear force. When we turn up the interaction strength, that means X gets smaller, so it's a stronger interaction. Here's the graph that we calculated with IBM's quantum computer. There are wiggles from quantum effects, but overall what you see is the red curve coming down and the blue curve going up. This says that in the beginning, our glue ball was on the left side of the lattice. High probability of finding it over here on the left or red side of the lattice. But after enough time has passed, red has a small probability. The glue ball is now on the blue or right side of our lattice. And that's what we wanted to see, a real particle made of gluons or strong interaction moving from one side of the lattice to the other. And to get this far in time, to get this many time steps, we had to use the error mitigation that we've been discussing. So here's my last slide. This method of error mitigation allowed us to get good results, even on today's noisy quantum computers. And let me mention that the people who build these computers do a fantastic job. I mean, they're noisy because it's really difficult, but progress is extremely rapid. You might ask, can we already today go ahead and do something more realistic? Can we put in the quarks? Can we have 3 colors, just like nature, instead of only 2? Amazingly, we can already say yes to this because in the past 2 weeks, July 6th and July 8th, 2 separate groups have done this very thing. One group is working at the University of Washington in Seattle. Professor Martin Savage is there with this group of excellent scientists, 3 of whom are students. And here's a 4th student. His name is familiar. Sarah is the undergraduate student from York, who happens to have a summer job in this group at Washington. And the other group is centered at the University of Waterloo in the Institute for Quantum Computing. Christine Mushik is the professor there. You'll see my name as well. I've been collaborating with these people and a long list of excellent people, some of whom I have collaborated with before. Sieglinde actually works for IBM in Germany, and Victor is a student at McGill who is spending his summer in Waterloo, an outstanding student. So as you can see, several students are involved in this work. Progress is happening quickly. Maybe it's something that interests you as well. I'll stop there. Thanks very much for your time. And if you have any questions, ask away.
Okay. Thank you so much, Professor, for this wonderful talk about how to use quantum computers to simulate elementary particles. We will now move on to the question and answer period, which will not be included in the recording, which we will upload on our YouTube. So I'm gonna stop